drink.
Hey guys.
Oh. I'm Jeremy.
What up? I'm Nick. I'm Jeff Wood. Today our project is going to be on the Come Along Winch, and Nick, you want to tell them about this?
Yeah, I got it.
Cheers, buddy. All right, hey Jeremy, let's go. Hey guys, the winch is a mechanical device consisting of a spool, a crank, and a cable or wire. A winch is usually used to reduce the weight of a lifted object, especially when usage is combined with a pulley system. More specifically, a come-along winch is a mechanical tool that consists of a lever arm that ratchets to adjust the slack or tension in the cable. Like all winches, the come-along spools the cable tightly with the crank, but unlike some other winches, it will not move the cable in alternating directions as the ratchet locks the cable in place, acting as a brake. Come-along winches are commonly used for their convenience, as many can be carried by hand. Winches have been used for thousands of years. The oldest written document describes how wooden winches were used to tighten cables for bridges in 480 BC. Aristotle acknowledged the fact that winches were a common used tool in architectural work. Early systems like this lead to the types of systems we use today. They vary from the same mechanical winches used in ancient times to the industrial rigging equipment practiced right here in Puget Sound Naval Shipyard. Because the come-along winch is usually used in conjunction with a pulley, weight of the load is reduced significantly. Often the force required to move the crank is fractional to the weight of the load. Alright, so now we're going to show you how the come-along winch works. And it, Jeremy, you know which one?
Yeah, I'll go.
Alright, cool. No, not a winch.
I told you he read this one.
Yeah, one of those.
You didn't specify. Alright, we're
sorry.
good. Thanks.
Alright, sorry about that. Alright, so now we're gonna hook this guy up here. Alright, let's see what this procedure here in the lab tells us to do. Okay, so first part of the procedure here, just gonna hang the come-along winch. We did that already. We're gonna go ahead and put our weight in there. Our first weight, instead of using kilograms, we're gonna go ahead and use these weights we have here. We've got a 10-pound weight. We're gonna stick it in the bucket. And we're going to make sure that the distance from here to here is 12 inches. I'm going to measure that real quick.
Got a total height of 36, right?
Yeah, and yep, that's about 12 inches right there. Okay. From the floor to the bottom of the bucket is going to be 11 inches. And from the bottom of the ground to the bottom of the handle is 36 inches. That'll be what we're starting with. And now, I'm going to pull on this to see how much force it takes to lift this bucket. I'm going to start pulling it. And it looks to be about 2 pounds of force all the way through. So now Jeremy's going to go ahead and measure the length of the arm move.
We come to 65 inches.
Okay, and on the bottom of the bucket, you see that one more time. Looks like we moved 1 inch. So it took 2 pounds of force to lift this 10-pound bucket.
Alright, so now we're going to calculate our IMA. We've got the lever arm in over the lever arm out, which is going to be 15.75 inches. Over 2.76 inches. I'm just going to give you a 5.71. Let's see, this is going to be second one, because you're going to take all three and you're going to multiply them all together to get your final IMA of the winch. You're going to have the distance of the wheel. In this case, it's going to be where the ratchet is, and then this is going to be the cable spool. And so you're going to have 3.54 inches over 3.15. It's going to give you a 1.1. And then your third factor is just going to be the number of supporting lines. Since you had the bucket suspended, it was just the two. So then you're going to multiply this one to get your winch. You're going to end up with 12.6. IMA distance is going to be your distance in over distance out, which basically is just the 27 inches it took to move the lever arm from the top to the bottom. Alright, now we're going to go ahead and calculate our actual mechanical advantage. And you're going to have, for the first one, we got force out over the force in, which is going to be 10 pounds, because that was the first weight. Over 2 pounds, that's what it took to lift the lever arm up, which is going to give you 5. For our second one, is going to be the 15-pound weight over the 3 pounds it took in order to move that lever arm, also 5. And third one is going to be our final, which was the combined weight of this, of 40 pounds over 4, to give you 10. We can go ahead and find our work now. We got the work in is going to be your force in times the distance in. Alright, now we found our IMA, found our AMA. We're going to go ahead and find the work in. So we got the force times the distance. So you end up with the 2 pounds that it took, 3 pounds, and the 4 pounds, all the lift it, the 27 inches. So the 2 times 27 is going to be 54. Let's see, it's going to be 81. And then the 4 by 27 is going to be 112. So we're able to go ahead and find our workout. And that's the 1 inch that the bucket had moved up. And then these are each of the weights. So obviously it's going to be 10, 25, and 40. For our efficiency, we've got the work out over the work in, and we've got it for each 3 set. So we end up with, first one's going to be the 10 pounds over 54 down here, which is going to give us 19. We've got the 5 over 81. Oh, sorry, that's going to be 15. It's going to be 31. And then we've got the 40 over 112, which is going to be 36. So we're going to take all these and we're average them, which is going to give us average of 29% efficiency. So that's the first efficiency. Then for our second one, we're going to have the AMA over the IMA of the winch times 100%, which is going to be the 5 over 12.6. That's 100. It's going to give us 40%. And so you see we got our efficiencies and then all of our work calculated. That's our calculations.
Alright, so some of the advantages of a come-along pulley would be you have a larger output than your input. It's also pretty small, pretty mobile. You can carry it just about anywhere with you. Some disadvantages are your output is limited to the strength of the person doing the input. So, I mean, it's also only one direction. It only lifts, so you can't really lower things. So once it's up, it's up. You have to drop the weight, you can't lower it back down. Some of the efficiency losses would be due to friction or human error when calculating efficiency. Something you could do to improve the efficiency would be adding more support lines.
And now we're comparing the difference of efficiency between the IMA distance and the IMA winch. We believe that the IMA distance is more accurate because with IMA winch you deal with the length of the lever arm input to what you get output. You deal with the diameter of the spool, and then you also deal with the number of supporting lines, which leads to more reasons or causes due to human error. As for with the IMA distance, after 3 trials, all of the lengths were the same for how much you put in for distance of the lever arm to what you got out of it. Did the IMA distance vary with the weight differencing? No, it did not, and I think the reason why it didn't really change much is because we didn't have a lot of weight, and that's probably one thing. If we have more weight to it, we could possibly see it changing more. Now we're comparing the differences between N1 efficiency of N1 and N2. The discrepancies between the two is that N1 is more accurate because you only have to deal with your work in and your work out, so there's less cause for human error. Again, with N2 you're dealing with the AMA and the IMA, which has a lot more room for human error. So in that case we found that N1 was more accurate. We're going to suggest some changes that will help the procedure flow a lot better. Some changes we feel that can help out with this experiment is because we didn't work a lot of weight in with our experiment, the tension between the line wasn't very tense as it could have been. So therefore we can, due to human error, friction loss, all that stuff, we lose a lot of efficiency through that. So if we put on more weight, have the line more tense, that can create better observations and calculations through our work. Another thing we could do to change the procedure is add more supporting lines, which could also help out our efficiency, our input and our output ratio. I'm Nick.
I'm Jeremy.
I'm Jeff.
That was our presentation on the come along winch. We hope you learned something, and we'll see you next time.